Yeah, so like Max said, my name's Tony Gentilcore, and this is James Simonsen. We both work on what's called the Chrome Speed team, and basically our team's mission is to act like a ratchet for Chrome performance so that we're continually getting faster and not regressing. Also to understand full stack performance and suggest ideas for optimization, and finally to develop the tools and infrastructure and documentation to make the entire team more productive at working on performance. So today, basically, since our tools have been changing so rapidly recently, and we've been doing a lot of interesting studies and everything, what we wanted to do is James is going to give an overview of how to dive into a specific performance problem with tracing and how to use tracing to dive into that. Then we're going to transition, and I'm going to talk about telemetry and what you can do with our performance testing framework telemetry. And finally talk about some of the studies we've been doing about where the main thread actually spends the bulk of its time while it's loading web pages. Finally, if you have questions, I think we're gonna just flip to this moderator page at the end. So as we talk, pop them in there. Also, feel free to interrupt us. We're hoping to leave a solid 10 or 15 minutes at the end for questions. Hopefully that'll work out.
All right, so I guess the first question to start off with everything is, what is performance? So as software engineers, I think we have a pretty good idea of what we think performance is. In general, we think of things like benchmarks, right? And so there's sites like Tom's Hardware Guide that runs benchmarks periodically. They do their web browser Grand Prix, and they say browser X is the best at this, browser Y is the best, and so on. So if we go off metric, we see that we're actually doing a pretty good job, right? We got a Blink browser #1 on the list here. Pat ourselves on the back, good job. And we're done, right? So next talk. So actually, users generally don't think too much about benchmarks, right? They don't run benchmarks. They can't really tell. I think we had like a 20-point advantage on that last slide. Nobody can really feel what the difference is in 20 points there. What they feel is what they see when they're browsing the web, right? So let's put ourselves in the mind of the average user. So for example, let's imagine we're an oil baron, okay? And we happen to like milkshakes and bowling. And one of the things we do as an oil baron in this modern age is we attend oil conferences, right? Much like we attend conferences here, right? So, as everybody knows, the best site for learning about oil conferences is .com, right? So I was going to click on this link and give you a live demo of how much we suck at oilevent.com, but it turns out the site is down and it's serving server errors. So I cannot show you in person, but I encourage you to try tomorrow and see. Basically what you'll see is 15 seconds of blank page and spinner. Finally we'll do it, and then you have 30 seconds of page frozen, can't scroll, can't click on anything. Basically it sucks. So this guy's mad. He's not a person we want to make mad. So what can we do to figure out what's wrong here and how do we fix it? So the tool that we think is the best for analyzing what's going on in the browser kind of as a system is tracing. Okay, and I've got a link here. We'll send out the slides later. You can check it out. But I think the best way to actually explore tracing and learn about it is to just dive in. So let's do it. Let's do a little bit of a live demo here. So first of all, you go to tracing real simple. Just go to about : tracing. I was hoping it would autocomplete, but it didn't. And then there's this record button here up in the corner, right? So just click that. In general, the default settings are just fine. So go ahead and click record. And then now it's our chance to do something interesting that we want to record. So let's check the news. And we wait for the page load. Okay, that's got some content on here, and we stop our trace, and it's going to load this in. And I will show you how to navigate tracing and how to see things in it. It takes just a second for this to pop up. All right. Okay, so I know this is like kind of crazy looking at first, but I will explain it to you. That is why I'm here. So first of all, what we're looking at here is a timeline. So on the left is when we started the trace, and time advances to the right. Okay, that's easy. Vertically, what we're seeing is we're seeing the different processes here. So here you probably can't read it, but it says browser process right there. And then that you have Is this cutting out? Should we try this one? He said not.
Oh, it turned it up.
I'm going to try this. Hello? Hello? Okay, we'll try this one. So anyway, so we were looking at the browser process, and then these blocks inside here are the different threads, okay? And we can scroll down and see all the other things going on here. And I wanted to scroll down to the point where we see the renderer processes. This is probably the one I'm looking for there. We have CNN.com right there. Inside the renderer, we've got the different threads. We've got the compositor going on. We got the renderer. And we've got the IO thread and the parser thread. So those are the things we expect to see. So anyway, we've got these weird looking boxes here in the middle, and we want to figure out what those are. So I need to teach you how to navigate this. So this was written by people who play first person shooters. So WASD. So we can zoom in with W. Navigate, sidestep right, sidestep left, and get a little strafing action in there. And we can zoom in here and see things going on. And basically for each individual thread, so we're looking at the main renderer thread here. So this is our main thread. And it's divided in two halves. So the bottom half here is what we call the synchronous events. So these are things that block the CPU. These are things that are running, basically. So this purple bar here means we're pretty much chugging through the CPU nonstop here. Each one of these events is kind of nested vertically. So as we're going down here, we're seeing like nested function calls. So of course, everything starts with the message loop run task. That's our basic primitive. Here, we're handling an IPC message. So that's what this one is. If you would click on it. That's not clicking on it. Anyway, take my word for it. Oh, it just chugged for a bit, and now I lost my place. Crappy. This is why live demos suck. Anyway, okay, there we are. So we're handling this IPC message here, and then as part of that, we have to compile some JavaScript, and then a little bit later on, we're going to run it. Let's zoom in a little bit more on this one. We can see there's some other things that are going on in here, and we'd be able to click on these points here and see that, I guess these are new instances here, not super exciting. But anyway, we're seeing what's going on. So we got a script compile and execute, and then we've got another script compile and execute, another script compile and execute here. This one's got some interesting stuff going on here. We're sending IPCs. We've got a recalc style in here. And then outside this, we've got another recalc style here. And then because we're doing that recalc style, because the very next thing we're going to do here is here's where we're going to begin drawing a frame on the screen. Okay, so you're kind of getting a gist of what the browser or what the renderer process is doing. We're compiling all this JavaScript. You can imagine the parser chewing through this, running the scripts. Now we've got enough content. We want to do a layout, so we do the recalc style and layout here. And then we're going to draw the frame on the screen, and then we've got more scripts to run, and we'll go ahead and start doing that. So this is basically what you're looking at with the main renderer process. This is our CPU consumption. So the second half, though, of this thread is these kind of lighter colored boxes up here. So these ones here. These ones we call asynchronous events. So these are things that don't necessarily block the CPU, but kind of go on in the background. So the prime example here, of course, is loading the resources. So you can see we're loading the main CNN.com resource here. As that starts downloading, we're going to notice there's some CSS and JavaScript we have to fetch. So that's what these ones are here. And eventually we're going to get to the point where we start downloading ads and images and things like that out here. So that's what it's showing you here. And kind of an interesting thing you can see, so this section here is where we're loading the JavaScript and the CSS and whatnot, and you can see that is in fact where we're compiling and running the JavaScript. So you can kind of make that correlation to what's going on, the cause and effect there. So that's kind of a basic overview of tracing there. Let's see how we can actually identify and tackle problems using tracing. So I got some examples here for you. So let's get back into the presentation. Okay, so I recorded this load over the weekend, happens to be ESPN.com here. And one of the things I noticed while I was looking at all these resource loads, which I just showed you, is that there's this kind of interesting phenomenon here where there's a bunch of resources that all finish loading right along this black line here. And that seems a little suspicious to me, because when have you ever seen these resources all fetched at different times? They're going over a network. Some of them are different size. It sure seems odd that they would all complete at exactly the same time, right? That just doesn't really make any sense. So what I did here is I scrolled to the top where I saw the browser process. And the browser process is, of course, the one that's actually making the network request. So we get the IPC from the renderer saying, I need to load this resource, and it loads it. And sure enough, you see that it actually finished loading a lot of these resources much sooner. So that black line lines up, but there's nothing finishing there. Everything was done much earlier back here. So why does the renderer think it took so long to fetch this resource when the browser said, hey, I was done a 10th of a second ago? So the answer is to look at the main thread for the renderer. And it turns out it was blocked. The main thread is what's going to handle the responses as IPCs from the browser process, but it was busy running a V8 callback. In this particular case here, in this callback, I clicked on the sync channel and did a reverse lookup of the codes there, and it was loading the local storage database, basically. And that's synchronous call. We're just blocking because JavaScript needs it, and we're just stuck there waiting until it comes back. And so because of that, we're getting all this network activity back. We could have been drawing stuff. We could have been decoding images, but instead we're just sitting here waiting. So this is a place where we have main thread contention. And so obviously when we're talking about threading and stuff like this, this is the sort of thing we're talking about avoiding, okay? So here's another thing we can do with trace. We can do, gosh, hello? I think we're just gonna have to make do. So we're comparing two different traces here. So we have one trace at the top that yeah. Hello. Okay, well, this one. Do we have an alternate? What's our plan? It's turned off, apparently. We could. Can we do that, Max? Okay. Sorry, technical delay here. Take a time out. Have a drink. We have a wire.
Hello?
It's kind of short. That's okay, we're good. Hello? Okay, it still works. Okay, we'll just run with it. So anyway, yeah, so another thing you can do with tracing is you can kind of compare two traces and see what the differences is. So this is good if you've got like two different flags or two different versions, you want to see what's different. So on the top, I've got the software rendering path. On the bottom, I've got the composite rendering path. I showed you how you can click on one of these and see how long it takes. So you can see software path takes 40 milliseconds to do the paint. The composite path takes 66 milliseconds. The thing I'm actually interested in, though, is because I care about page loads, is I want to see what things are slowing down the page load performance. And so, of course, we want to chew through the JavaScript as quickly as possible. And you see there's a bunch of JavaScript we run here, same JavaScript run here. And then there's another script that runs after this paint and a script over here that runs after this paint. But you can see this one's much later than the one up here. So part of it is because it takes longer to do the paint here. But another interesting thing is there's this sync channel thing in here, which looks unusual. And we don't really see anything here. Maybe there's something here, but it's just a tiny little sliver. So let's investigate this and see what's going on here. So what I can do is I can do the selection tool. That's the fourth tool on the menu. And you can select this region here and then kind of inspect it across all the different threads, okay? So we've got our sync channel selected here. Let's scroll down to the compositor and see what's going on during that time period. And you can see, sure enough, it's busy doing something. But this looks kind of suspicious, just to me as somebody who's looked at this a lot. You guys will catch up with this stuff eventually. But, I mean, sorry, that sounded really mean. I didn't mean that. I just mean, yeah. So anyway, you start learning to see what's familiar and what's not. So anyway, the thing that looks suspicious here is we have a bunch of things that take almost no time, right? And then all of a sudden, the same activity takes a ton of time, 25 milliseconds. So something unusual is going on here. Like, why is this thing that's normally instantaneous taking 25 milliseconds? And the answer is you have to scroll all the way up to the browser process here. And you see it's busy doing something. It turns out this trace here was taken on a single core machine. So what's actually happening is these things here are probably instantaneous. But because the main thread is, or the main browser process has the CPU and is busy doing something, nothing else is running. And so it appears that these things are taking much longer than they otherwise would. So what we're showing here is we're showing CPU contention, right? So when we talk about threading things, like we should just create as many threads as possible, this is the downside of that. Not everybody has as many cores as we have threads, right? And this is how you identify it. You'll see things that take longer than they should take because the CPU is descheduled during that time, okay? So we've got a couple examples here of things you can catch with tracing. So I know you guys are all super excited to go home and try this, right? So yes, that's awesome. Thank you. So here is how you add tracing to Blink. It's super easy. We just have these nice macros for you. So down here, you just have a trace event. You specify the category that you want. That category, I don't know if you remember, when I first clicked record, there's a dialog with a bunch of checkboxes. You can toggle these things on and off. That's what the category is for. And then just the name of the slice. This is demonstrating a synchronous event. So this is basically something that's chewing up CPU. And so for these ones, they're just basically scoped to whatever C++ scope they're in, right? So we're basically measuring the duration of this memory cache prune call here. So that'll automatically start and end at the right time and show it on the trace. The other one you have is the asynchronous events here. These ones, they can't be scoped to something because that doesn't really make any sense, right? Because they're going on in the background. So you have to explicitly say when I'm starting, when we're advancing, and then when we're done. So I've got the three different macros here. The only thing that's unique about these ones is they take a third parameter here, which is the unique identifier. And typically we use a pointer because that's usually pretty unique, hopefully. So anyway, and then one other thing, I don't know if you noticed, but on some of the slices, when you click on them, there's some kind of extra information like the URL of the resource that was loaded. You just pass those in as the extra parameters here. You specify how many of those you want. You can have 0, 1, or 2 extra arguments here. Give them a name and then the value, and then it'll show up on your trace when you click on it. So super easy, okay? So let's go back to our oil baron and figure out how we can make things better so he doesn't beat us with a bowling pin. So in this example here, this looks like a pretty typical trace, right? I mean, we're doing a bunch of layouts. They get incrementally long, they get longer as there's more information being loaded in. And so, we kind of expect that sort of thing. But what is unique about this trace is the time scale of it. So when I click at this layout here, this is a 28-second layout. This was recorded on a Z620. This is a super fast machine. So you can imagine what your phone is going to do on this sort of site, right? It's just going to explode. So this one isn't even the longest layout. I should have clicked on this one. This one's even longer. And you can see the tracing just cut off. It gave up. It's like, we're not going to get anywhere. So this site is really slow. So we know we're burning through a lot of CPU in layout here. So we've got a couple of ways we can try to identify the problem further. One is to just add tracing. And if I knew the layout system really well, maybe I would know like, oh, I should trace this function because that's probably expensive. And I trace this function, that's probably expensive. And maybe I'd see which one of those ones ends up being the long pull. But I don't really know the layout system that well, so I'm just going to fall back to just straight up CPU profiling. So we've got a link here. You can click on it and read about how we do profiling and Blink and whatnot. But I just used my favorite profiling tool, which is pprof. You can see there's a bunch of just random noise up here. But basically, there are two things that are dominating the entire thing here. And they basically add up to 80% of our CPU time in these two functions. And both of them happen to be in this pod free list arena. So now it's time to just get in the code, roll up our sleeves, figure out what's going on here. So turns out this site has 7,000 floating divs on it. That's an awesome way to design a site. And so for each one of those floating divs, they end up in the place floats tree when we do the layout. And these things are allocated, these tree nodes are allocated from this pod free list arena. And so every time we construct the tree and then we throw it away because we're going to do a new layout, we have to free all those tree nodes, right? And it turns out that when you're doing when you're freeing those tree nodes, we have this vector of all these different free lists here, and we don't know exactly which chunk and which free list the freed node should go to. So we do a search every single time. So for all 7,000 of these, we have to do this linear search through all the chunks. Do you have the one I'm looking for? Do you have the one I'm looking for? Okay, great. And then send it back to the free list. That seems a little bit wasteful. We could probably just keep track of which one we came from, and then we wouldn't have to do this search. So the patch actually ended up being real simple. Just replace this search here. just keep track of which one we're supposed to add it to and just add it directly back. That's how we got all our performance back. Interesting little tidbit here. We were doing this linear search to find which one was the one we should add it back to. We don't break after we actually found it. So we might have been able to exit early, but no, we didn't. So anyway, Simon Hatch was the one who found this and fixed this. I'm basically just relaying his story because he's on vacation in Hawaii right now. So we should all feel very, very, yeah, this was worthy of it, right? So anyway, I've shown you now how you can do a deep dive using tracing and profiling, find a serious issue that's affecting our users, something that will be kind of a decision maker. If somebody's using a Blink-powered browser and it just sucks that much on one page, they're going to switch, right? No matter how great our benchmark scores are. So we have to think about the long tail here, right? And how we can make things great for everyone. So I've shown you how to do that, and then now Tony is going to take it over and show you how you can find other sites that have problems like this and move on. It looks like we got a couple questions. Maybe we'll take a couple questions now, and then I'll turn it over to Tony. Go ahead. Yeah, there's a page. So on that very first, on that slide, so we sent it, I'll post the slides or whatever. On that slide that mentioned Chrome tracing, there's a link to the documentation there. It'll be in there. Another one back there. Oh, did we tell them to fix their website? No, I don't think we should actually, because if you load it in the other browsers, it's instantaneous. So it's really a Blink specific or Blink/WebKit specific problem. So, okay, question here. Couldn't have what on Android? It does work, and Tony's going to explain it. Oh, you can't, you do it over ADB and all that stuff, but yeah, you can definitely get it. So he'll explain it. Anything else before we move on? Okay, Ken? I don't remember. Do you remember the speed up?
It was like an order of magnitude.
Yeah. And then, okay, 20 to 1.7 sounds like. Good. Okay, great. Yeah, order of magnitude. Last question. Yes. Tony's going to talk about that. You guys are like super smart and like way ahead of us. So we'll get to it. So just a sec. I'm going to turn it over to Tony.
Yeah, that was pretty hard to follow. That was awesome. So the first thing I want to talk about is, so we dove into one specific case. And so I kind of want to get a picture of how do we find these cases? How do we know what to optimize? I'm hoping to pose more questions than provide answers. But first of all, because all of our performance tooling and infrastructure has been changing so rapidly recently, I just wanted to use this opportunity to talk about what telemetry is capable of today and what you can do with it to measure performance. For those of you who aren't familiar, telemetry is Chrome's performance testing framework. This runs anywhere where Chrome runs. So it runs on Android, it runs on Chrome OS, runs on all of our desktop platforms, and it runs against Content Shell, it runs against Test Shell, it runs against the full Chrome app. So you can basically connect via the DevTools protocol to anything that exposes the DevTools protocol, really. And so what I'd like to talk to you about with telemetry is kind of walk through how we can use it to create a micro benchmark, how we can use it to turn an individual web page into a benchmark, and finally, how we can use it to turn the entire internet into our own benchmark. So the first thing you can do with telemetry is create micro benchmarks, and this should be pretty familiar to people who have worked in WebKit. This is basically what run perf tests does today. So with telemetry, we can run all of the run perf tests beyond the bug that someone pointed out earlier that apparently we're not passing the right flags to enable all of the testing APIs. But you run the run measurement script, and telemetry is kind of based around this idea that you have a page set, which is a group of things that you want to measure, and you have a measurement, which is what you want to measure. So we have a measurement in this case called BlinkPerf that knows how to run the what is it called, perf test runner framework that we use in the Blink performance test. So here basically I've run the URL parser benchmark, and you'll get a column for every time you run that benchmark. and you'll get the values, and it'll give you a point on the graph for every run. And if there's a statistically significant difference, which there isn't here, it'll tell you what the statistically significant difference is in the run. We've been making a couple little like minor cosmetic changes to this since pulling it from run perf test. You can now like delete an individual column, which is really helpful when you're doing multiple runs, and you can rename columns just by clicking on them. So we're trying to take it even to the next step from where the run perf test was. But more interesting, so I think there's definitely a place for micro benchmarks, but I think more interesting is to like have a real world web page that acts like your benchmark. So telemetry relies on a system called Webpage Replay, which is basically a web server that is a map between HTTP requests and responses. And what it does is you run it in record mode and it watches everything that goes by, and then you run it in replay mode, and in replay mode, it knows the answer to every HTTP request that it has to give. And I'll gloss over it, but there's actually a lot of heuristics and intelligence that goes into making this work for real world web pages. We have to sub out math.random and date.now for deterministic implementations. We have to do fuzzy matching on query string parameters, things like that. So basically, this is the first step. This is the very first thing I do when I start working on a performance problem. If I want to make a web page faster, I run this record WPR script on the URL, so I get a stable copy to benchmark against. Because if you don't do this and you try to benchmark against a live site, network changes from run to run, and that like is way bigger than the performance improvement you're working on. Ads rotate that are changing the performance characteristics. Like you just can't you can't properly optimize a site without getting a stable version of that site. So once we have this benchmark, once we've run record WPR, it spits us out this www.google.com.json file, which is a recording. And so now we can run any of our measurements against that recording. So we have measurements for like profiling and the DevTools timeline, for tracing that James showed to spit out a trace, for memory, for measuring frames per second, smoothness. We do this for like scrolling the top 25 sites and measuring frame rate on those. But once you run the benchmark, then the next thing you need to do is to actually profile it. So telemetry will spit out if you pass -- profiler equals blah, it'll spit out a profile for the interesting segment of the benchmark. And so we can tell it. So what I like to do when I'm looking at traces is, rather than like manually hitting trace myself and stop in the UI, and somebody asks about how to do this on Android because you can't really use the UI there, I always just record the page and then replay it here with -- profiler equals trace. Somebody else asked about like power earlier. So we recently added a Monsoon profiler, and a Monsoon is this device that does Android power measurement. So if you happen to have one of those physical devices, telemetry will talk to that thing and give you the power utilization numbers. But yeah, you can read those or ask me about those later. Finally, somebody asked about how we run these on bots. So I think the ideal situation when you go to optimize something is that we create this repeatable benchmark, and then we put it on a bot and we run it there so that we can guard against regressions in that code, and we can like track and brag about our improvements. So like when Simon first started to work on these tough layout cases, he created a set of pages which he recorded that he called tough layout cases, which are all sites dominated by layout time. And the very first 50% fix. So like this is like one of the sexier perf graphs that I've ever seen, because it tells a really great story. So there's that initial huge fix, which included the oil event, which actually we talked about it like it's just oil event, but this affected any site with a lot of floats. So it affected several sites in here. And then we see several like 5 and 10% improvements after that. But the other interesting thing we see here is there was a regression. And what happens there is anytime these regress, we have a rotation of performance sheriffs who get alerted. And so these people are always, on their rotation where they look at all the alerts of any time a graph moves the wrong direction. They get this little alert, and then they triage that. So they assign it to a bug, and it's annotated on that graph forever. And you can see here we regressed, and then soon after that regression was reverted, and we continued marching down. So this is what we want to see from our performance tests. finally, the last thing I promised is how do we turn the internet into a benchmark? So Ravi Mistry of the Skia team has created this great web UI where basically you punch in a telemetry measurement that you want to run, and you can run it against the top 1 million web pages. These web pages have a recording, so you're not going to spam the web pages. They're all going to pull from the stable recording. You should be able to do comparisons that way. It runs on 100 machines, so it takes about 12 hours to crank through a million pages. But basically, you can set this up if you have some question to answer. Like the other day, Julian was asking me, should we optimize layout for wide DOMs or for deep DOMs? So you can, with like 2 lines of code, you can write a telemetry measurement that spits out statistics about the depth and width of the DOM, and then you can run the top 1 million sites and get back all of your data about the shape of the DOM. So the final thing I'd like to talk about, let me just take a time check. How are we doing? 10 minutes. Is what should we optimize? So in my mind, the central theme right now that we should think about is give the main thread back to developers. This is big because it improves page load time, it reduces jank, and it improves responsiveness. And so how do we go about deciding what's important in giving the main thread back to developers? So the question we need to know is, in the wild, in the real world, what's actually running on the main thread at any given point in time? So the first thing we did was run the loading measurement, which takes all of the DevTools timeline events and tells us how long we spent in each category on Linux with the top 1 million sites. And here, what we see is the first and third events are both JavaScript. And so right now, devs have 39% of the main thread, which is pretty good. We'd like this to be basically 100%. Anything we're doing on the main thread is like stealing from the app developer. And so when we first started to look at this, it looked like layout is the most expensive thing in Blink, and that's what we need to focus on. But there are some problems with studying page load on Linux, and that's Android is actually our highest priority platform, and so that's where we should be looking at these optimizations. We should be targeting them at Android first. And second, Eric Seidel found out that Linux actually had a pathological font loading condition where font loading on Linux was much slower than other platforms, and so it was actually overinflated. And the other problem with studying Linux is that Linux kind of uses a 2-year-old graphics stack. I think Tom and Ned will talk more about this, but what I've seen is mostly like we launch things first on Android and then next on Windows, and then, you know, I haven't actually seen most of the cool stuff get onto Linux yet. So we're really not getting the most accurate view of page load time by studying Linux. So the next thing we did, we had to scale this down quite a bit because we didn't have the 100 machine infrastructure, is run the top 25,000 sites on Android, the same experiment, and find out where we spend time there. And at first blush, you look at these results, and it looks like Rasterize is our #1 priority, and we should be working on nothing but Rasterize time. But when you dive into this a little bit more, that's not actually what's going on. So the Rasterize is running on a new thread. In this case, it's not actually running on the main thread time. And it includes descheduled time. So this thread isn't actually scheduled and burning CPU for the whole time. And also in this particular experiment, we used real network conditions. So we could be blocked on the network and like running an animation that's doing a lot of optimization. So instead, what I really think falls out of this is our highest priority should be to understand thread contention better. I would like to get a better picture of how many cores our users actually end up having on average. Like what are we dealing with? How many threads should we actually have? Because I'm not sure that like just moving everything to a new thread is a panacea. So let's look at it again, but this time completely ignore the Rasterize time. And here what stands out, if you remember on Linux, only 10% of the time was uncategorized, but now the biggest segment of time, 20%, is uncategorized time. So I think our next really high priority item is to categorize the uncategorized right now and understand where this additional time is being spent. This isn't being spent in the systems that were very highly optimizing, like layout and such. This is basically unknown time. So I started to look into this a little bit, and part of this, a big part of this is V8 context initialization time, which Jochen recently made a big fix for by snapshotting the I18N API. Basically, before his change, it was like we were executing 150K of JavaScript in every new frame. So this was taking up a lot of time. So I think this is my final slide. Basically, what I've said are these are some of the big questions on my mind. So I think understanding thread contention better is really important. Categorizing that uncategorized time and understanding that better is really important. We see next that layout still is 10% here, and presumably what we're going to see is we're going to break down the uncategorized time, and that's all going to fall into smaller things. And so layout is going to be a long pole here. So I think just driving down layout time is important. Understanding the received data contribution, you would naively think that this received data, which is like getting bytes off the network, should be really fast, and we're spending almost as much time there as layout. And so the question is kind of what's going on there. Driving down parse HTML contribution. So we measure the parse time measured here is actually only the time on the main thread, not the tokenization on the other thread. So this is like attaching the nodes to the DOM and such. And we saw like really big improvements here with some of the lazy attach work that's been going on. But I think understanding what the main thread is still doing in relation to parsing is important. And then the next thing, the final thing is that I think recalc style actually doesn't even show up on this Android profile, but I think we're going to categorize some of these things better, drive some of them down, and then I think the next thing we'll see poke its head into the profile is recalc style. So that's it. Right, that's a good point. So the observation is that uncategorized time is too big right now. When we ran this experiment, we used the DevTools timeline to get the categories and not tracing. And so we have the facilities and telemetry now. Actually, Nat Duca added a measurement that reports that uses tracing instead of timeline to break down. So I think we're going to get when we run that study, we're going to get a much more precise answer to what's going on. We'll actually be able to say like what is V8 compilation and what is V8 execution versus just what is V8 run. So I'm really excited to run this with tracing. I'm also really excited to run like the smoothness measurement to see where we're spending time during scrolling instead of where we're spending time during loading. Yeah, so the next observation is that if we only report things that are traced, we're going to miss things. So I think there's a couple things we can do about that. So we set as one of our goals for the upcoming quarter to add trace events on all the important things that are uncategorized. So right now we're basically like we have a few patches in line to add some key trace events to make all this time understandable. But basically we're like binary searching through the code. We're kind of like adding a trace event right under the top one and then adding two more and just figuring out where the time is going. So I think right now, I think you're absolutely right. The exact problem is we don't understand where the time is going because it relies on developers. So we'd like to get traces around the events that we need traces on. For what it's worth, I sent this to Blink Dev. I ran the same experiment with the perf profiler so we can see at a function level where we're spending time. And so that's another way to look at it. I actually didn't have as many takeaways from looking at the perf data. Like I found it a little bit harder to be actionable. But maybe we can find like basically I guess the key point I would like to get across is we have a lot of great infrastructure to run experiments like this right now, and I would like everybody thinking about like what what are the things we should be measuring? Like, what experiments should we design? How can we do this better? How can we learn more? Is that fair? Okay. Max's suggestion is we halt questions and identify topics for performance breakout sessions. I know Nat had an idea for one. So yeah, Nat's idea was to have a deeper dive on about tracing tomorrow. Does anybody else have things they would like to cover? Eric? Eric suggests a performance lab where people come with questions and then people who know the tooling help figure out how the tools can answer those questions. Other ideas? John? The question is, oh, go ahead. Are you finished? Yeah, so the question was, we have this infrastructure for running these measurements with performance over the top million sites. Could we do this for correctness? So could we say, like, run a patch and see if it changes the rendering of the web, if I understand the question correctly? I think that we probably could. I think it would be some work. The reason Ravi originally wrote the framework is to gather SK pictures. So one of the things it does is it saves SK pictures for all the websites that it goes to. So I think we could probably like come up with a differ for those and just report the differences. Since it's running against recorded versions of the web page, we should be able to control for like ad content changing and things like that. So I'd be curious to see this investigated further. Dominic? The question is, can this infrastructure be used for things other than page loading and scrolling, like editing? What else? Resizing. That's a good question. I don't think we have a good way to do resizing right now. Yeah, Nat's shaking his head too. And editing, I think we probably could. I think it would be a matter of writing the measurements that are interesting for editing. I mean, do you have Blink performance tests for editing right now? So like the types of things that they're doing, we can generalize those measurements so that they could run against an arbitrary page and then stick it out against whatever page set we want to measure it against. In the back here. This is a great question. We've seen a lot of CPU measurements. Are there memory measurements? So telemetry has memory measuring and profiling. It's hooked up to the deep memory profiler that some folks have been working on that gives you this breakdown of where you spent all of your memory. So like I myself am primarily interested in speed and not memory, but I wish more people were interested in memory. And I think there's some great tooling here to do the same kind of studies, but figure out where memory is going over the top million sites. I would absolutely love to see that happen. Yeah. Basically, I mean, if you want to chat afterwards, I think we could just submit a job to the web form that would measure that now. Greg has another good point. We have another tool called Chrome Endure, which is designed for long-running measurements. So this is like open up Gmail and click compose, discard for hours and hours on end and see how your memory usage changes. And this is all, telemetry is kind of the infrastructure for running Chrome Endure now. And so that's another way where, depending on the scenario, if the scenario you're interested in is like load a page and look at usage, that's one thing. If the scenario is interact with an app repeatedly and see where the leaks are, then Endure is much better for like leak detection. Another one here. The suggestion is that we have a breakout session on latency instead of throughput. Is this like input latency, or is this like okay. Dirk?
How much of this stuff that you talked about is especially with the million page thing, is available to people outside of Google?
Oh, yeah. Ravis Framework works for anyone with an @Chromium or an @Google account. So that's pretty cool. Anybody can run this. I guess maybe I should like slightly caution these tests aren't free. They're going to tie up the framework for 12 hours. So if right afterward, like we basically haven't figured out how to scale it yet. So maybe it was a dumb idea to announce this at this conference. If everybody goes and like ties up all the bots, but for now, until it breaks, anyone with a Chromium or a Google can kick off a job. Eric?
How do I get involved as a random Blink dev user? Where do I know what's going on in this? How do I, where's the list? How do I get involved?
Eric says, as a Blink developer, how do I get involved in these sorts of efforts? If you're talking telemetry specifically, there's a telemetry at chromium.org list. If you're talking anything Blink related, I really think we should keep performance discussions on the main Blink list. We've avoided wanting to create a performance specific list publicly there. Like we do have an internal performance list for Googlers where it's like, you know, we talk about why a Google property got slower or things that aren't appropriate for external, but anything that's involving the open source project, I'd really like to keep on Blink Dev. Do folks agree, or what do you think? Yeah. In the back? Okay. Yeah, so the question was, could we get more info on the perf sheriff process and what they're doing? I was gonna pull up the dashboard, but maybe I'll just talk through it. There's so the performance sheriffs basically use this dashboard where they start with a list of the current alerts. So this just shows all the tests we monitor across all the different platforms. There's maybe a dozen alerts that aren't triaged right now, and so their job is like, let me pick a big one. This one's 70%. So they basically, you know, the perf sheriffs don't always know Blink that well. Some of them are even new to the project, so they're not like able to look into all of these issues directly. But pretty much what they do is they click these alerts. The alert tells them that there was a change in performance here, and then they can click on the point and see the list of all the changes that went into that. If you want to see the Blink changes, you click here. And what the performance sheriffs pretty much do is they click this, they file a bug, and then they click the bisect button. And we have bisecting tribots that will basically go and create a build at every one of these revisions and figure out which patch actually caused that regression. And so, like, I'm sure a lot of people in this room have heard from a perf sheriff at some point in time. So their basic idea is just to triage and diagnose all of the performance regressions and then make the author aware of that. And Chrome has had since the very beginning a no performance regressions policy. So we hope that in any case we can accomplish the feature or accomplish what we're trying to do without actually having to regress performance. Okay, we're gonna break here. We'll chat more in breakout.